Hello everyone, welcome to our channel Everyday Learning. So in today's video of digital logic design, we are going to study about 3-bit asynchronous binary counter. Now before I move on to the stages or the functions of the 3-bit binary counter, which is asynchronous, I would like to brief a bit about counter and then about asynchronous counter. Counters can basically be of two types. One is ripple or asynchronous counter and the other one is synchronous counter. Now we shall discuss only about asynchronous counter in today's video. So an asynchronous counter is also known as a ripple counter, and for it to be asynchronous, there is a special part, which is the external clock that you can see over here is only connected to one flip-flop, and the other flip-flops get the edge triggering or the clock transition from its previous immediate flip-flop. Now as you can see here that the first JK flip-flop used here has only the external clock, and the output of the first JK flip-flop coming out from the Q0, it is from the Q0, that is the opposite of the Q, acts as the clock for the next flip-flop in the sequence. And similarly for the third one, the second one's Q0 output acts as the clock for the third one. Since this is a 3-bit binary counter, we will require 3 flip-flops, and we have used JK flip-flop to design the asynchronous 3-bit binary counter. Now there are also subsections, like there can be up counter, down counter, or combination of counters. Now we shall design an up counter for today's asynchronous design, and the disadvantage of asynchronous counter is related to the propagation delay. This is to be kept in mind. This is the disadvantage. Now let us move on to our lesson of 3-bit counter, which is asynchronous. Now we can see that there is a common input which is connected to each input JK of the 3 flip-flops that are present, and they have individual outputs Q0, Q1 and Q2. Now Q0 is the least significant bit here for our counter, and Q2 is the most significant bit here, and that is stated in the state sequence. Now let us move on to the timing diagram, and we can see that we have 1, 2, 3, 4, 5, 6, 7, 8 clock transitions or clock cycles here. Now for the first one, that is indicated by Q0, we can see that it was initially reset or in low condition, and whenever the clock was applied, the input high was taken in by the JK flip-flop and it became high. And in this sequence, as the clock kept on ticking, the sequences changed from 0 to 1 after each clock transition. Now if we come to the second output, which is related to the second JK flip-flop, we have to notice that the duration for the clock cycles has increased. So it is observed that the duration has doubled. Now why is it so? It is because the second flip-flop and its transition is dependent upon the output of the first flip-flop. It can only be triggered or transitioned after the first flip-flop gave out its output. So we can see that due to this dependency, the clock duration for the second output has already delayed. Now if we move on to the third one, the third flip-flop, we can see that it is doubled than the previous one, as it took 2 to produce the second one. Now it is taking 4. So it has doubled from the previous one, and this is understandable, like the same concept that for getting the clock pulse in the third flip-flop, the output of the second flip-flop is necessary, and this output acts as the clock for the third one. So the clock duration increasing can be understood pretty easily due to the asynchronous property of this counter. So the propagation delay disadvantage can be easily proved with this timing diagram and can be explained as a result. Now let us move on to how it is producing the sequence starting from 0002 3-bit, which is up to 7. Now we'll just have to match it like this. We go from low to up. So at first sequence we have 0 0 0. So we write it here. Initially it is 0 0 0, and we get this one when there is no pulse, when there is no clock pulse. Now for the first clock pulse, it will produce the sequence 0 0 1, and in this way for the second one it will produce 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Now you might wonder what happens for the 8th clock pulse. Now we can see from our timing diagram that at the 8th pulse the counter recycles and reaches its initial state, which is again 0 0 0. So it recycles at the 8th position. Now we can term this one as asynchronous binary up counter. So in this manner the counters work. I hope you could understand how the 3-bit asynchronous binary counter has to be designed and why there is a propagation delay due to the dependency of the clocks, and how the sequences are generated and finally recycles to its initial position. You can refer to our Logisim tutorials of the counters from our playlist that is available in our channel, and then you'll be able to also get a practical idea about it. So we'll end this video here. I hope you are able to understand the concept. So thank you for watching our video.